Welcome to the first lecture for Physics 1111K, which is also Introductory Physics 1. Here we start with lectures 1 and 2, which we'll cover with the first chapter, that is kinematics, the study of motion. So to define motion, let's start with a coordinate system. So let's start with something called the Cartesian coordinate system, which is named after René Descartes, the French philosopher. So let's look at this picture here. We have this picture of René Descartes, and we have this fly in the picture. And we are trying to figure out the location of this fly with respect to René Descartes' head. Okay. So we have the coordinates of the fly. So this is what we are trying to find. And then we have another fixed point, which is the reference point. That's Descartes' head. Okay, so this gives us the general framework that when you want to define the position of an object in terms of coordinates, x and y coordinates, you need to do that in terms of some reference point, a fixed point here. And you can look at these two examples down here. So the first example says that someone is standing 7 feet from the front wall and 20 feet from the left wall. So here the positions are 7 feet and 20 feet, and the reference are the front wall and the left wall. Okay, and then we have the next example. Someone is sitting on the 3rd row from the front and 5th column from the right. So again, we have the two positions here, 3rd row and 5th column. And then they're measured from two references, the front and the right. Okay, so either way, you have to define a reference point first, and then from the reference point, you can measure the coordinates of other points in the system. Okay, so let's start with a simple Cartesian coordinate system, which is in one dimension. So we start with the 1D coordinate system. And what does the 1D coordinate system tell us? It tells us that whatever object is in the system, it can only move along a straight line. So the one dimension refers to a straight line on which this object is confined. The object cannot go outside the straight line. So this straight line is the dimension is the single dimension, and this constitutes one-dimensional motion. So here let's draw a straight line. So you can see we have this line here, and it is not necessarily horizontal or vertical. It's a straight line, that's it, but it doesn't have to be perfectly horizontal or perfectly vertical. It can be in any direction. And we have this fly on this straight line here. So we are going to consider the position of this fly as it moves along this line. So this fly is moving in one dimension, and let's try to define its coordinate. So as we discussed in the previous slide, we need to have a reference point defined somewhere. So this is the straight line here. The reference point has to be somewhere on the line. So where on the line do you define it? Okay, so we can choose any point. And so let's choose a reference point somewhere. Let's call it 0. And then on the right of 0, we mark positive numbers. So you can see that towards the right, we go in positive values of x, going towards higher positive values. And then on the left side, we go to negative values of x. Okay. All right, so this is how a one-dimensional coordinate system is defined. You have to choose a reference point somewhere. That's going to be your 0. Okay, so this is a reference point. Okay, and this reference point, we call it x equals 0. So that's the usual convention. The reference point is chosen at 0. Okay, and on one side you have positive values, and on the other side you have negative values. Okay, so we call them directions. We call them the positive direction and the negative direction. Okay, so let's get back to the fly here. So the fly is on this line on the tightrope. So suppose we choose a reference point somewhere, and the fly turns out to be 2 units, so 2 centimeters on the right of the reference point. So the position of this fly is x equals 2. Okay, so that's the position of the current position of the fly, x equals 2 centimeters. Now, what does x equals 2 centimeter mean? It means that there's a reference point at x equals 0, and then it means that if you go 2 centimeters in the positive direction, you'll end up where the fly is located. Okay, so in other words, the fly is located at 2 centimeters from x equals 0 on the type road along the x direction, along the positive x direction. Okay, so for example, if we had x equals -2, then it would mean the fly is located 2 centimeters in the negative direction. Okay, so that would be 2 centimeters on the left of the origin. All right, so we come across an important concept here, that when you introduce a coordinate system, it automatically gives you a positive direction and a negative direction. All right, and we have 0 right in the middle, so the 0 divides the positive and negative numbers, and you can figure out the direction by looking at the opposite sides of the reference point of 0. Okay, so we choose locations on the right to be 0, that's the convention, and we choose locations on the left to be negative. Okay, so look, values on the right of the reference is positive, values on the left of the reference are negative. All right, so here's an example of a negative value for x. So we have this fly at x equals -5, which means it's on the left of the reference point and it's at a distance of 5 units from the reference point. All right, so again, the directions are important. So positive direction, negative directions tell you where the positions are with respect to the reference point. Okay, so here are the 2 tips here. You always specify the origin of the coordinate system. That means you choose a 0 point and you choose a positive and negative directions. Usually the right is taken to be positive and left is taken to be negative of the origin. Okay, so technically you can choose whichever direction you want. You can choose left to be positive or right to be positive, but usually we take right to be positive here. It's just convention. All right, and here are the 2 illustrations of the fly at a positive position and a negative position. So this quantity x is the position of the fly in this one-dimensional coordinate system. And as we said earlier, it doesn't matter if the line is not horizontal, so we can have a line that's vertical here, and in this case we can still use the one-dimensional coordinate system. We still have to choose an origin, we still have to choose a positive direction, and then automatically we choose a negative direction as well. So this is what the coordinate system would look like for this line here, for this vertical line. You choose a 0 somewhere, the origin, and then usually we choose upward to be positive. So you can see all these numbers going up are positive, and then all the numbers going down below the origin are negative. So the fly here has coordinates of y equals 5 centimeters and y equals -7 centimeters. Okay, so we are using the symbol y to represent position. Okay, so x and y are really the same thing. It's just that x usually means a position in the horizontal direction, and y usually means a position in the vertical direction, but they both represent positions. Okay, so x and y are both symbols for representing position of something. Okay, so we have studied how to define a position in a coordinate system. Now let's move on to the next topic, the concept of displacement. So what's displacement? It's the change in position here. So let's underline the word change, it's important. Okay, so earlier we looked at just the position, the quantity x, and now we are looking at the change in position, so how much x changes. So let's look at this picture at the top. So we have this coordinate system and we have this fly. So the first position, the initial position of the fly is x equals -5 centimeters. So that's where the fly is marked. And then the fly moves. It ends up at a different position, x equals +2 centimeters. So that's the current position. So the position of the fly has changed, and the amount it changes by, that's known as the displacement. So displacement is the change in position, and the symbol for displacement is this delta x. So this symbol delta, so here you can see the note written on the left. So that triangle is known as the delta, a Greek symbol, and it usually represents a change in something. So here we have delta x, that means change in x or change in position. And how do you find the change in x? So the change in x is this expression, the final position minus the initial position. So x final, x initial are the positions at the final and the initial. and when you subtract them, you get the change in the position. So should point out that the change of anything, so delta of any quantity, is represented by an expression of this form: the final value of the quantity minus the initial value of the quantity. In this case, we are looking at position, so we put delta x, so we get x final and x minus x initial, but it applies to any quantity that's changing. Okay, so we have an equation here, an equation for finding the displacement. So let's put this in a box here. And now let's look at this question underneath. So we have an equation for finding the displacement. So let's get back to the fly. So what's the displacement of this fly? All right, so we can use this equation to calculate the displacement. So we have to plug in the value of x final and then subtract the value of x initial. And then whatever we get, that's your displacement delta x. Okay, and this is the work shown for the displacement. So here we plug in the values for x initial and x final. Oops. So for x final, we can see in the picture, the value is positive 2 centimeters. All right, so we have positive 2 centimeters plugged in for x final, and then for x initial, we plug in negative 5 centimeters. Okay, the sign is important, the negative sign. So when you plug in 2 centimeters for x final and negative 5 centimeters for x initial, and you subtract them, you can see that you end up with subtracting a negative sign. And we know that when you have two negative signs, it gives a positive sign. So effectively, you have 2 centimeters plus 5 centimeters. That gives a total of positive 7 centimeters. Okay, and here, you have to be careful about the sign. The sign is important when you're calculating the position or the displacement, because we'll see that the sign tells you which direction the displacement is taking in. So here we have positive 7 centimeters of displacement, which means the following here. Okay, so let's highlight this part. Positive displacement means the fly is moving in the positive direction. So positive 7 centimeter displacement means the fly is moving 7 centimeters in the positive direction, which is to the right. Okay. All right, so to the right is another way of saying positive direction. Okay, then let's look at this slide here. So in the previous slide, we calculate the position and displacement, and we used a one-dimensional coordinate system. Okay, so let's take this one step further. Let's introduce something called the particle model. So in this model, we capture the position of an object at different instants of time. So here we have multiple pictures of a car traveling to the right, and we captured the position of the car at different times using snapshots. So you can see in the note in the parenthesis, it says that each car represents a snapshot taken after 1 second interval. So looking at the snapshots, we can determine the position of the car. So at the initial snapshot, so let's call this time 0, the car was at this location. And then at time 1, the next snapshot, at 1 second, it's at this next position here. Then after 2 seconds, it's the third one, and so on. So this is known as a particle model. It shows you the position of a particle at different points in time. Okay, so here we have what we call the motion diagram of a car, and this motion diagram consists of multiple snapshots. And underneath, we have the motion diagram using the particle model. So just the difference is that you replace the picture of the car with a dot, with a particle. Okay, so it makes it simpler. So you can see it's the same information as we had above, that at time 0, the particle, the car, is at this location here, the first dot. At time 1, it moves to the next dot here. And then at time 2 and 3, it keeps moving to the right. So looking at this picture, we can figure out both the position of the car and the times when it's at this particular position. So this method, this motion diagram with the particle model gives us more information than just the position itself. We get the position and the time both. All right, so here's more information here. So here we have a particle model, the motion diagram of particle model, and each dot represents the object and the number underneath represents the time at which the snapshot was taken. Basically, it shows you the position at each time recorded. And always we start with time of 0. Okay, let's put a note for this. You always choose a starting time of 0 because it makes your calculations easier. Okay. All right, and then the next dot, the subsequent dots show you the position of the object at the subsequent snapshots, and the object is represented by a single dot every time. Okay, and the number underneath shows you the order, so effectively shows the time at which the snapshot was taken. Now let's look at the distance between dots. Okay, so for every two dots, every two successive dots, the same amount of time elapses between them. Okay, so the time between 0 and 1 is a certain amount of time, and the time between 1 and 2 is the same amount of time. So the same amount of time elapses between consecutive frames. Okay, so looking at the picture, we can figure out the time it takes to go from 0 to 1, from position 0 to position 1, and then from position 1 to 2, and so on. And then looking at the gap between them, the distance between the dots, we can figure out the distance traveled. Okay, so we can figure out the displacement and the time from this picture here. Okay, so it gives us the displacement and how quickly the displacement is taking place. So here, this brings us to the next concept, the concept of speed. So that takes into account the distance traveled and the time taken. So this tells you how fast something is moving, how quickly or how slowly something is moving. That's determined by speed, because it takes into account not just the distance traveled, but also the time taken. And in this box here, you can see the equation that we have for calculating the speed. So speed equals the distance traveled in a certain interval divided by the time that time interval. Okay, so we are factoring the distance traveled and time to get the speed. And here we have two pictures here, two motion diagrams. So the first one shows you the motion diagram of a car from 0 to 3 seconds. So we have these 4 snapshots starting from 0 second going up to 3 seconds. Okay, and we can see the snapshots are equally spaced. Okay, so this tells us that it's traveling the same distance at every interval between the dots here. Okay, and then underneath we have a motion diagram for a bicycle. Again, it shows the motion from 0 to 3 seconds. And then we also have a one-dimensional coordinate system underneath. So we have the reference point 0. It starts at where the car and the bicycle were located initially at time 0. Okay, so that's going to be a 0 position as well. And then using the coordinate system underneath, we can figure out the position of the car and the bike at different times. So we can see the car is traveling from 0 to 40 meters in 1 second, and then from 40 to 80 meters in 2 seconds, and so on. And the bicycle travels a smaller distance. So in 1 second it goes from, in the first second it goes from 0 to 20 meters. Then in the next interval it goes from 20 to 40, like this. Okay, so this motion diagram, we can use it to find the positions of the car and the bicycle as well as the time, and then combining we can find the speed. So that's what we are doing down here. So we are finding the speed of the car, and let's put a bullet point here. So to find the speed of the car, you take any 2 points in the motion diagram. Could be the first and the second, the first and the third, the second and the third, second and the fourth, doesn't matter, any 2 points. So you take the 2 points, find the coordinates, the position of the particle at these 2 points here. So for the car, let's pick a time of 1 second and 2 seconds, the 2 dots. And at 1 second, you can see the position is 40. After 2 seconds, the position is 80. Okay, so you take these two numbers, 80 minus 40. All right, and then you subtract them to find the distance. Here, I'll just work it out somewhere. So on the slide, it shows you 40 meters. So where do you get the 40 from? We get the 40 from subtracting the displacement at the initial time from the displacement at the final time. So this is this 40 meters is the distance traveled. So you take the final position x final, subtract the initial position x initial, okay? And you can choose any 2 points, choose one of them to be x final, one to be x initial. So here we have chosen 2 seconds as our x final and 1 second as our x initial. So we have to find the corresponding distance at 1 second and 2 seconds. So plug in the numbers now. X final is 80 meters. X initial is 40 meters. So subtracting them gives you a distance traveled of 40 meters. So that's where the 40 meter comes in. And then you're dividing by 1 second. That's the time interval between the dots. So when you divide the 40 meters by 1 second, you get 40, and the unit is meters per second. Okay. So the meters per second is the unit for speed. So let's put a note for that as well. So later on, we'll discuss what units are. So units are quantities for measuring different values. Okay. So here we have the quantity speed. Okay. So this tells us how fast something is moving. But if we just say that the speed is a certain value, like if the speed is 10 or 20 or 30 or 100, so sure, it tells us that we have a certain speed here, but it doesn't give us the speed in terms of real quantities that we can relate to. So you have to introduce units here. Okay, so unit, we have units of meters per second for speed. So this is telling you that if the speed is 40 meters per second, this object will travel 40 meters in a time of 1 second. Okay, so the unit is important to define the magnitude, the strength of something. So here it tells you the speed is 40 units, 40 meters per second. That's how strong, how big the speed is. Okay, so there are other units you can use as well. So for example, you can use 40 centimeters per second. So if it were 40 centimeters per second, the object would be traveling 40 centimeters in 1 second. That's a lot less than 40 meters. So the unit effectively tells you the magnitude, how big the quantity is. All right, so for speed, the unit is meters per second. And we get that as we have seen in the calculation here. You divide 40 meters, so you carry the unit of meters with the distance. You divide by 1 second, so second is the unit of time, meter is the unit of distance. You subtract, you divide them, you get meters per second. All right, so the speed of the car is 40 meters per second. Then let's repeat for the bike. And for the bike, we again choose 2 points. Doesn't matter whether it's the first 2 or anywhere in the interval. So you choose 2 points here. So x initial and x final. And here we choose them at 1 second and 2 seconds again. Let's label them. Okay. And when you subtract x final and x initial, so when you do x final minus initial, you are doing 40 minus 20. Okay, for the bike. And that gives you a distance traveled of 20 meters. All right, so in this interval chosen, the bike travels 20 meters in 1 second. So you divide 20 meters by 1 second, you get 20 meters per second. That's the speed of the bike. And as expected, the car has a bigger speed, so it travels faster. It just goes at 40 meters per second compared to 20 meters per second for the bike. And as we can see in the picture, in the motion diagram, the car is... Okay, so we covered speed. Now, the next topic, let's look at velocity. All right, so what's velocity? So velocity is this quantity here. It's a displacement divided by time. Okay, so you can compare with the equation for speed. Speed is distance divided by time, whereas velocity is displacement divided by time. All right, and we'll look at the difference between displacement and distance later. So for now, let's put a note here that displacement gives you not just how far something travels, but also in which direction. Okay, so let's put a note here. Okay, so displacement takes into account how far an object travels and in which direction. Okay, so it can be a positive direction, negative direction, but whichever direction you specify, but that has to be accounted for in the displacement. Okay, so for example, if we say the displacement is a positive number, like positive 5 meters maybe, so this tells us the object is moving in the positive direction 5 meters. And if it's a displacement of the negative 20 meters, so that tells you the object is moving 20 meters in the negative direction. Okay, so here we are still doing one-dimensional coordinate system. So you can only have two directions, positive or negative. So again, put a note for this. All right, so in one dimension, you can account for the direction pretty easily. Just put a positive sign for the delta x or negative sign, that takes care of it. And later in the semester, later in the course, we'll look at 2 dimensions, and it's more complicated because you have to account for multiple positive and negative signs. So if the displacement can be positive or negative, then you can look at the equation for velocity. Velocity can also be positive or negative depending on the sign of the displacement. So you can look at the examples here for the 2 motion diagrams. So we have bike 1 that starts from the left and moves to the right. Okay, and then we have bike 2, starts from the right, moves to the left. So both these bikes travel the same distance in the same time, but they're traveling in opposite direction. So we can look at the coordinate axis down here. Bike 1 is traveling in the positive direction, bike 2 in the negative direction. So you can calculate their velocities. They will have opposite velocities. Bike 1 will have positive 20 meters per second. So you can take the total distance, 120 meters, divide by the 6 seconds, you'll get 20 meters per second. And bike 2 has negative 20 meters per second velocity. So we say both bikes have the same speed, because speed doesn't take into account direction, but they have opposite velocities. All right, so that's the difference between velocity and speed. So velocity accounts for direction. All right, so differences here between displacement and distance. So displacement depends on only the final and the initial position, and it doesn't depend on what path you're taking. So you have 2 points, let's say A and B, and displacement is just the B minus A or A minus B. That will be a displacement. Just take into account the final and the initial position. So it doesn't matter whether you went straight from A to B or went through a curved path or however else, the displacement remains the same. And displacement can be positive or negative. Okay, and then distance, it depends on the length of the path taken. So to draw an example, so let's say this is our initial position. Okay, and this is our final position. Let's call it x final. Okay, and the path that you take looks like this maybe. Okay, so you're not going straight from A to B. You're going by some curved path. Okay, so your distance is going to be the actual length of the path, right? So that's what's going to distance be, the actual length of the path taken. So if you take a different path, your distance changes. Okay, let's write this down. However, displacement is just the straight line distance from x initial to final. Okay. So displacement is just x final minus x initial. Okay, it doesn't matter what path you take to go from final to initial. What matters is your final position and the initial position, and you can subtract them to get the displacement. All right, so that's the difference here. Distance is the length of the path. It can only be positive, but displacement is final minus initial positions. It can be positive or negative. Okay, so if you have a, so you can have take different paths to go from x initial to final, but and then we have velocity versus speed. So like we said earlier, velocity can be positive or negative. It has direction. And like before, like in the previous slide, velocity only depends on the final and the initial velocities, initial position, sorry. Okay, it doesn't depend on the path taken. But speed depends on the length of the path taken. So you can look at the two equations here. To find velocity, you divide the displacement over time. And we already know about the displacement is from previous slides. You just subtract the final and the initial. But to find the speed, you take into account the distance, which takes into account the length of the path taken. Okay, and speed can only be positive, velocity can be positive or negative. So velocity has direction involved in it, which is what the positive and negative signs tell you. Okay, so example of the velocity and speed here. So this object starts at 1 meter at x equals 1 at time of 0. Then it goes to the right up to x equals 3, then x equals 4. But then it turns around and keeps going until x equals negative 1. Okay, so we say at time 2 seconds, we have a turning point because the object is changing direction. It was going in the positive direction, and then at 2 seconds, it changes to a negative direction. So let's find the speed between 0 and 4 seconds. So to find the speed, we have to factor in the total distance covered. So how do we find the total distance? We add up the length of the path of all the pieces. Okay. So let's start with 0 to 1 second. It goes 3 meters. Then from 1 to 2 seconds, it goes 1 meter. 2 to 3 seconds is going 2 meters. Okay. So the distance traveled is 2 meters from 2 to 3 seconds. The displacement is negative 2 meters. But here we're interested in distance. So I'll just write 2 meters. Then the last part from 3 to 4 seconds, you're going 3 meters here. So add them all up. We'll get 3 plus 1 plus 2 plus 3. Okay, got to correct this. This should be 2 meters, not 3. Okay, and that changes our calculation. Okay, so the first segment from 0 to 1 second should be 2 meters. I wrote down 3 initially. Okay, so we have 2 meters plus 1 plus 2 plus 3. That gives you a total of 8 meters. So that's the distance traveled. Okay, you divide by the time, 4 seconds, you get the speed of 2 meters per second. All right, so we found the speed. Now for the velocity, you don't take into account the distance, you take into account the displacement. And how do you find the displacement? Just take the initial velocity. Here, let's write this down. So initial position is this, x initial equals 1 meter, and your final position is whatever is at 4 seconds. So x final is negative 1 meter. Okay, so you can see I'm just taking into account the initial position, the final position, and not the path that you're taking. So it doesn't matter whether you're going to the right first and turning around. What matters is where you start and where you end up. So that's what we plug in into the equation here for delta x. For x final, plug in a negative 1. And for x initial, plug in positive 1. So you're subtracting negative 1 minus 1. So you get a total of negative 2. Okay, so in numerator, you get a negative 2 meters as your displacement. You divide by the time, you get negative half. Okay, so note the negative sign here. So the velocity is negative. And you can see in the picture, the object starts at +1 and then ends up in the -1 here. So displacement was negative, so the velocity was negative. So it doesn't matter that it went to the right at first. The average velocity between 1 and 4 seconds. Now we have looked at motion diagrams. Let's look at other representations. So first we have the motion diagram. We have covered that already. You use the dots with position and time to represent the motion of the object. Another way is to use a table of data. So you can use the same data from up here, list them in a table, make a column for time and position. Okay. So the table of data has a lot of information, but you can see it's not organized in a way that's easy to read. It's in columns, and a reader has to read through the columns to get an idea. So the third way is probably the best one that we have here, a graph. So you draw a graph of position, x on the y-axis, time on the x-axis, and you draw a line or multiple lines to represent the position. So all three representations here give you the same motion. Okay, so it has an object. So a student starts at time 0 at position 0, then goes to this motion here, sometimes going fast, sometimes going slow, and ends up somewhere above 500 meters. And the graph shows you the same thing. So does the table, that the student starts at 0 and then has these different lines to represent different speeds, and then ends up at the final position of about 500, above 500. Now, before we continue, let's do this problem with motion diagrams. We have two runners, A and B. They both start at 0, position 0 at time of 0. And then runner A ends up slightly below 50 meters. Let's assume it's at 48 meters. So let's mark them. Okay. So this is time 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. So we have for runner A 8 seconds, and the final position, let's say, is 48 meters. Okay, so just make up a number, 48 meters. You can see it's pretty close to 50, so might as well. And then for runner B, we can mark the times again. So we have 0, 1, 2, 3, 4. Okay, 8, 9, and 10. Okay, and the final position is 50 meters. So the question is, which runner is moving faster? Who has bigger speed? So you took okay. So here, this is what we have. Runner A has a bigger speed. Okay, because to find speed, you do the distance over time. For runner A, we have a distance of 48 meters and a time of 8 seconds. And you plug them into the equation, you get a speed of 6 meters per second. But for runner B, you have a bigger distance, but also bigger time. So you end up with a smaller speed. Okay, you get a speed of 5 meters per second for runner B. All right, so runner A is faster, as we figured out from the calculation. All right, so back to graphs here. So let's look at graphs. So we said that we can draw a graph to represent position and time. So here, let's do this in more detail. So we have a table here, a list of times in the first column, a list of positions at the second column. Okay, and then we can find the velocities. So how do you find the velocities? We can here, we can take 2 points and then subtract and find the distance between them. So let's say we take these 2 points here. In these 2 points, we have time 0 to 1, and the change in x is 5 meters. Okay, so that gives you the third column, 5. And then to find the velocity, you divide this number 5 by the change in time, which is 1 second. Okay, So here, I'll just do the calculation. You have to do 5 meters over 1 second. Gives you 5 meters per second. So that gives us the fourth column. So you start with the columns of time and position, and from there you can find displacement and velocity. Just that to find displacement, you take 2 points at a time. Then the next one, let's take the next 2 points, 5 and 10, and do the same thing. We get a displacement of 5 and the speed of 5 as well. Velocity of 5 as well. Then you do the second at time 2 and time 3. Same process, you get the same displacement and velocity. And now after that, you get the next 2 data points. You get a bigger displacement this time. You get 15 rather than 5. And your velocity gets bigger as well. So this motion tells you that for part of the time, the velocity is 5 meters per second, and then for the other part is 15 meters per second. So now let's make a plot. Okay. So let's start with the plot of position versus time. So we use the data from the first table. Okay, so we use the data from this table here, and that gets plugged into the first graph. Okay, all right. So we take these points. So the first point is 0 and 0. So that's simple. Plot it at the origin, and then take the next point, time 1, position 5. Okay, so you have a time of, you go along the time axis for 1 unit, 1 second, then go up 5 units for position. Wherever you end up, you put a dot here. And you repeat for all the points in the table. So this is what we get for position versus time. So you can see that up to time of 3 seconds, we have a straight line, and then beyond that we have another straight line which slopes up further, slopes up more because this velocity is greater. Okay, so this is the position time graph. And then for the other graph we have So for the other graph, we are plotting the velocity. So here, this one column versus time. Okay, so the other column here. So they get plugged in, they get plotted into this graph. So now you consider all the time values and the velocity values. Okay, but you got to be careful because you don't calculate the velocity for each time. You calculate the velocity for like in between, you 2 points in time. So you make a plot for a time at the midpoint. So for example, you have time of 0 and 1. You're going to plot a time of 0.5. And then for the next one, you will plot a time of 1.5, then 2.5, like that. So you take the midpoints to plot the velocities. All right, and this is what we get. Okay, so you can see this is the velocity at 0.5 seconds, and 1.5 seconds, and 2.5 seconds, like that. Okay. So for the first 2 data points, you get a speed of 5 meters per second, as shown in the table, 4th column. And okay, so let's try this problem here. In this problem, we have a motion diagram of a car moving along a straight line. And let's look at the diagram here. So you can see that the first few dots are closely spaced, but then the dots get further and further, which means initially the speed is slow. So the car is moving slower, and then it speeds up. So we want to figure out which option here best describes this motion here. So let's look at the options. We are looking for a small speed initially, and then it jumps to a big speed. Okay, and you can see that the jump occurs at this data point here. So I guess in the 4th data point, the 4th dot at time 3. So we are looking for a graph that has a constant speed for the first half, and then has bigger speed for the second half. Okay, and there's a sudden jump at the midpoint at time 3. Okay, so looking at the options here, we can see that options A, B, and D, they all have lines that are sloping up, which tells us that the velocity is not constant, it's increasing. Okay, so we are plotting velocity versus time. So remember, whenever you have a graph, you look at the axis, figure out what quantities you're plotting. So here we are plotting velocity versus time, and the graphs A, B, and D tell you that the velocity is sloping up, so the velocity is not constant. Now for C, we have 2 straight lines, and then we have this jump in the middle. So that's what best corresponds to this motion diagram. So for the first half, the velocity is small. Then for the second half, it jumps suddenly and becomes large. And For both the first and the second half, the velocity is constant. It's not a sloping up, not changing. So C is the answer. Okay, now suppose we want to find the velocity from a graph of position and time. So we have this graph here, position on the y-axis, time on the x-axis. We have these data points, the dots here, okay? And we want to find the velocity from the position time graph. So what do we do? So let's start with this relationship. So if you have seen this already, velocity equals displacement over time, delta x over delta t. So let's pick 2 points from the graph and find delta x and delta t between them, okay? So let's pick any 2 points. So let's choose, let's say, these 2 points here in red. So we are finding the velocity in the second part here, the part that's sloping up steeper. Okay, so we choose 2 points on this part. So we have found the 2 points. We selected 2 points here, and then we find the delta x. So how do you find the delta x between the 2 points? So x is represented on the y-axis. So delta x would just be the difference in the height, the difference along the y-axis. Okay, so that's going to be a delta x. So find the height difference. So like draw a vertical line from one of the points all the way down, and the difference between the vertical coordinates of the 2 points is going to be delta x. And then you have to find the delta t, which is the width, the horizontal distance between the 2 points. So draw it like this, the black line. So essentially, you pick the 2 points, draw a vertical line, a horizontal line, and figure out where they meet, and draw a triangle. That's going to be that triangle is going to give you the displacement and the time. All right, so we got the delta x. We can just measure how high the red line is, and we can measure how wide the black line is. That will give us delta t. Then finally, we calculate v, the velocity. So it is delta x over delta t. But we have seen that delta x is the height, and delta t is the width in this graph. So effectively, we are doing velocity equals height over width. And that might seem familiar. That's the same as rise over run. And where have you seen this before? When calculating slope. So in other words, velocity is the slope of the graph of position versus time. Okay, so important relationship here. If you have a graph of position time, you can find the velocity just by finding the slope at every point. All right, so here, let's look at a special case. Let's look at something called uniform motion. And what does uniform motion mean? It means moving at constant speed. Okay, well, constant velocity, sorry. All right, so this object in the motion diagram is moving with a uniform velocity. It's performing uniform motion. So when the dots are equally spaced, okay? So this tells us when you plot a graph of position and time, your dots will be equally spaced as well. So you can see that all the dots, you space them equally in the horizontal direction, also in the vertical direction. And when you connect them, you get a straight line, okay? And as we have seen in the previous slide, the slope of this straight line gives you the velocity, okay? So that's in this other graph here. So you have this straight line, that's uniform motion. You take any 2 points on the straight line, so, and then find the slope. Whatever is the slope will be the velocity of this object, okay? And a reminder, if it's a straight line, it doesn't matter which 2 points you take. You can pick 2 points from the left side, from the middle, from the right, or from the 2 ends. As long as you pick them from the straight line, you'll get the same slope, okay? And that slope will be the velocity of this object. Okay, then now let's go the other way. So suppose we have a graph of velocity time. So velocity on the y-axis, time on the x-axis. So it's like this green graph here, okay, the horizontal line. So this object has uniform motion. It's moving at a constant velocity shown by the green line of 12 meters per second. So how can you find the displacement if you know the velocity? Okay. So to find the displacement from the velocity time graph, you do this. So you draw a rectangle So basically you find the area enclosed between the velocity line and the time axis. So in this case, it's this rectangle here. And this area under the velocity time graph gives you the displacement. Okay. All right, now got to be careful when you're doing this. So remember that the area can be positive or negative. Okay. All right, which means the area gives you a displacement, which effectively means the displacement that you calculate from the graph can be positive or negative, which makes sense because we know that depending on the velocity, you could have positive displacement or negative displacement. So if you end up with a positive area, which means that you're calculating the area above the time axis, you get positive displacement. So here, sorry, write this down. So here we have a positive area because the area is above the time axis. And then let's try another graph. Okay, so give an example of a negative area. So suppose we have a graph that looks like this: velocity on the y-axis, time on the x-axis, and the velocity time graph goes like maybe this. Okay, so it has is enclosed an area under the time axis. Okay, so this is the velocity time graph, and you can see it encloses an area under the time axis. Okay, and this is going to have a negative area. Okay, so examples of when area can be positive or negative, which means the displacement can be positive or negative. So if you have velocity time graph, you find the area enclosed between the velocity curve and the time axis, which can be which area can be positive or negative, and that will give you the displacement. Okay, remember this is the displacement, not the position. Okay, you get the displacement from the velocity time graph, not the position. So you can calculate how much the object has traveled in which direction. So let's try this. This problem here gives you a graph of position versus time for a basketball player. And the first half of the graph is flat, so the position is constant. And then the graph slopes downwards. So the player remains at constant position for some time, then moves towards the negative direction. So he starts at a positive x, keeps moving to a negative, goes to 0, and then keeps going in the negative direction here. So we are trying to figure out what the velocity time graph looks like. So reminder that velocity is the slope of the position time graph. So we have seen that already. So which tells you have to find the slope of this graph to figure out the velocity. So now this graph is made of two straight lines. Okay, so you have a straight line for the first half and the straight line for the second half. You have to find the slopes separately. So for the first half, we have a flat line, and we know the slope of a flat line is 0. Okay, so pretty simple. And then for the second half, we have a line that's sloping downwards, which gives you a negative slope. Okay, so we don't know exactly how much the slope is, but we know it's negative because you can see the line is going down. So we are looking for a velocity time graph that has that is 0 for the first half and has a negative value for the second half. Okay. And for both the first and second half, the slope should be constant. Okay, here let's put a note here. The slope is constant for both the first and the second half. It's not changing. Okay. Okay. So remember that here the position's changing, sure, but the slope isn't changing. This straight line has a constant slope. No matter where you measure the slope, like the middle or the top or the bottom, you'll have the same slope here. Okay. So we want a velocity time graph that is 0 for the first half and then has a negative value, constant negative value for the second half. And the one that fits the requirements best is option C. It has 0 velocity for the first half and has a constant negative velocity for the second half. Okay, so options A and B tell you that the velocity is not constant for the second half at least, and option D tells you, well, gives you the wrong direction. It tells you that for the second half, the player is moving in the positive direction with a positive velocity. Okay, so C is the answer that we are looking for. Okay, next question. So this time we have the velocity time graph. Okay, so notice the axis here. We have the velocity on the y-axis and time on the x-axis for a hockey puck. And the velocity is positive for the first half, then goes to 0 for the second half, which means the object is moving with a constant velocity for the first half and then stops moving for the second half. All right, so we are trying to find the position time graph here. Okay, so we know that the area under the velocity time graph gives us displacement. So let's write this down. Displacement delta x equals area under velocity time graph. Okay, so we break it up into two parts here for the first and second half because we have two straight lines. So for the first half, the area is positive. Okay, all right. And so the displacement should be positive, but there is more. We want to figure out how the displacement changes from 0, okay, to whatever this time is. Let's call it maybe t1. Okay, so we want to figure out how the displacement goes from 0 to t1. So we know it's going to be positive, sure, but we would like to know exactly how it changes. Is it a straight line? Is it curving or what? So to do that, we slice up the area into small parts like this, of let's say equal intervals. Okay, so kind of like this. So you slice it up into small pieces. Okay, maybe call them like T1 and T2 and so on. Okay. Okay, I'll just call this T something else, T final maybe. Okay, or yeah, just call it T final and then break it up into small parts here. So let's look at this individual small parts. Let's look at the first one. So this first small part has some positive area, sure, okay. And then this the next small part, okay, has the same area. So basically, all these small parts have the same area here, okay. And why is that important? This is important because it tells us that when you look at equal time intervals, so inside the first half you are looking at equal time intervals, T1, T2, T3, so on, the area is the same. So the displacement is the same for equal time intervals. Okay, you can break it up into as many time intervals as you want, as you can make the intervals small or big, and then find the area for all the intervals. They will all have the same area. That means the displacement is the same for all time intervals. Okay, so that's known as uniform motion, that you're traveling the same distance the same amount of time, and we should have a graph that's sloping that's sloping up in the positive direction. All right, so for the first half we want a graph that's sloping up, and for the second half we want a graph that's flat. Okay, so if you look at the options, so we have options B and D. Okay, both of them have the first part where the graph is sloping up, the position is sloping up, and then it reaches some final point. And then for graph B, the position goes back to 0, but for graph D, the position becomes constant. So look at the velocity time graph here. The velocity time graph says the velocity stops, which means the object stops. It doesn't say that the object goes back to the origin. So object just stays where it is. And that's why D is the right answer, because for D, the object moves with a constant velocity for the first half, and then when it reaches the final point, it stops, and the position should become constant. Okay, so earlier we talked about units. We said that quantities have to be measured in units to indicate how strong they are, so what quantities they represent. So we have some standard units that we use in physics. So altogether there are 7 standard base units. Okay, so what are base units? So base units are units with which you can represent the units of every quantity. Okay, so There are 7 base units in all of physics, and here we'll talk about 3 of them. Okay, so we'll talk about the units for distance, which is meters, and time is seconds, and mass is kilograms. Okay, so these are base units, and distance, time, and mass are base quantities. And then if you want to find the units of other quantities, you can find them using these base units. For example, if you want to find the unit of velocity, you look at the equation for velocity. You are dividing delta x over delta t. The unit of delta x is meters, and the unit of delta t is seconds. Here, let's write this down. So when you're dividing meters with seconds, you get meters per second. So that's the unit of velocity. And you can use this trick to find the unit of any quantity. So find an equation for that quantity, then figure out the units that go into the equation, then combine the units, you'll get your unit for the quantity. All right, and you will see that all units that you see in this class can be represented using meters, seconds, or kilograms. These are the base units. Okay, now next concept, we look at a non-uniform motion. So we look at the concept of acceleration. So earlier we looked at what happens when the velocity is constant, when the velocity is not changing, but now let's look at what happens when the velocity is changing. So if the velocity is changing, we say that the object is accelerating. Okay, so you can look in this box here. When the velocity of an object changes, when it's speeding up or slowing down, the object is said to accelerate. So how do you find the acceleration? You find it using this equation here. Okay, you divide delta v, so change in velocity over change in time, and you get the acceleration. So you can compare it with the equation for velocity. So velocity was displacement over time, so it was change in position over time, and acceleration is change in velocity over time. Okay, and how do you find the unit of acceleration? You can use the trick that we had in the previous slide. Acceleration is delta v over delta t. So the unit for delta v is meters per second. Unit for time, t, is s. So you divide meters per second by second. You end up with meters over second square. So unit of acceleration is meters per second square. All right, and here's some properties of acceleration. So acceleration tells you the rate of change of velocity, how quickly the velocity is changing and in which direction. So acceleration can be positive or negative. So positive acceleration means the velocity is increasing, getting more positive, and negative acceleration means the velocity is decreasing, getting more negative or less positive. And just like the way we found velocity from the position time graph, you can find the acceleration from the velocity time graph. The slope of the velocity time graph is the acceleration. Okay, so some properties of acceleration here. Okay, so here's an example of an accelerating object. So this car is moving to the right. So you can see the motion diagram. It's moving to the right and slowing down. So the velocity is changing, it's slowing down. Okay, so the velocity is positive. So for each of these dots, each of these points, the velocity is positive. Okay, because it's moving to the right, although it's slowing down, but still moving to the right. But the acceleration is negative. And we know this because the velocity is getting less positive here, it's slowing down. All right, so in this example, for all these points shown for all the car all throughout the motion, the velocity is positive. It's not negative here because it's still moving to the positive direction. But the acceleration is negative because the car is slowing down. So the velocity is getting less positive, but still positive, but just getting smaller. So it must be accelerating in the opposite direction. In other words, it must have a negative acceleration. All right, so this tells you that velocity and acceleration can point in different directions. It's perfectly possible. They can be in the same direction or opposite direction. And in this example, we looked at what happens when the acceleration and velocity are in opposite directions. Okay, so let's look at the graphs in this slide here. So this is an object that's moving to the right. You can see the velocity is positive and it's speeding up. So it's moving to the right and the velocity is getting more positive. So here, the velocity is positive and the acceleration is also positive. So if you draw a motion diagram, you'll see the dots will be getting the gaps will be getting bigger and bigger as you move to the right. Okay, so this is an example of both velocity and acceleration being positive. Okay, so let's write this down. So velocity and acceleration are both positive in the first graph. Okay. Then the second graph, we have a object that has a positive velocity, but you can see the velocity is getting smaller. So it's slowing down. It's still positive, but slowing down. So it has a negative slope. Okay, so the acceleration is negative, and the motion diagram looks like this. Okay, so dots are getting closer and closer, but they're still moving to the right. All right, so this is an example of positive velocity but negative acceleration. So kind of like what we saw in the previous slide. Third example, the object starts with a negative velocity and the velocity is getting closer to 0. So we say the velocity is getting more positive, and you can see the slope of the line is positive here. So the acceleration must be positive. All right, so this object is moving in the negative direction but slowing down. So the motion diagram looks like this. It starts from this dot here on the right. Then you can see that it's moving to the left, but it's slowing down because the dots are getting closer. Okay, so here we have a negative velocity but a positive acceleration. So the second and the third graphs, they have opposite velocity and acceleration, and you can see in both cases the object is slowing down. They're slowing down in different directions. So one is in the positive and the negative direction, but either way they're slowing down. Okay. And then the fourth example, we have a negative velocity, and you can see the velocity is getting more and more negative. Okay, so it's speeding up in the negative direction. So it has a negative slope, which means a negative acceleration. So the dot starts from the right, and you can see it moves to the left, and the spacing gets bigger and bigger. Okay, so here we have acceleration, velocity both in the same direction, both in the negative direction. All right. So the positive and negative directions, they always represent directions. So it applies to velocity or acceleration or displacement. So here we can see what happens if the velocity and acceleration in the same direction. That's the first and the fourth picture. And then what happens when they're in opposite directions, the second and third picture. So the object either speeds up if they are both in the same direction, and the object slows down if they're in opposite direction. Okay. All right, so it's summarized down here in this box. Now let's look at another special case of free fall. So what's free fall? Free fall means an object is released and you allow it to fall freely towards the ground. And once you have released it, there is no other external entity acting on it. So you're not pushing it, you're not touching it, there is no air resistance acting on it or whatever else. It's just free falling only under the influence of gravity. So that's what free fall is. Falling towards the ground only under the influence of gravity and nothing else. So it turns out that when you release an object and it free falls towards the ground, it has a constant acceleration. You will see that this object will travel faster and faster as it approaches the ground. So its velocity is changing, and the velocity is changing at a constant rate. It has a constant acceleration. And how much is the acceleration? So if you measure it, it turns out to be negative 9.8 meters per second square. So if you make a graph of velocity and time for this free-falling object, it will be a line that's sloping down, and the slope will be negative 9.8 meters per second square. And the negative sign means that it's pointing down. Okay, so we say that up is positive, down is negative. Okay, so the acceleration is pointing down, which means your object will get travel faster and faster as it approaches the ground. Okay, so important number to remember, negative 9.8 meters per second square. That's the acceleration of free fall. And it always points straight down, vertical downward. It's never going to point up. So it doesn't matter whether you throw an object up or down or in any direction, left or right. The acceleration will be this number, constant. Okay, so the velocity can be different, of course, depending on which direction you throw the ball. But the acceleration is going to be the constant number here, acceleration of free fall. So let's look at some velocity and time graphs. Okay, so this is what we know. So if you have a position time graph, you can find the slope to find the velocity. Okay, so we have seen this already. So if this red arrow goes from position time to velocity time graph, And then if you have velocity time graph, you can find the area under to get the displacement. So this green arrow goes from the velocity time to the position to the displacement graph here. Similarly, we can do graphs for velocity and acceleration like this. So if you have velocity time graph, you can find the slope to get the acceleration. And if you have an acceleration time graph, you can find the area under to get the change in velocity. Okay? So important here, when you find the area under, you find the change, not the actual velocity, but the change. So not exact value of v, but just the change in the velocity. All right, so this is what we have. Position time goes to velocity time, and velocity time goes to acceleration time. And going the other way, acceleration time under area under gives you a change in velocity, and the area under the velocity time graph gives you change in position displacement. So using graphs, you can. All right, so this is the full picture here. Position time relates to velocity time, which goes to acceleration time. In the other direction, the area under gives you change in velocity and then the change in position. Okay, now let's look at particular values of acceleration. So what happens if the acceleration is 0? So if you have an acceleration of 0, your acceleration time graph will just be a flat line, this black line you can see on the time axis. That means 0 acceleration. And we also know if acceleration is 0, it automatically means the velocity is constant, not changing. So your velocity time graph is going to be a flat line. Okay, so here we find the area under the acceleration time graph, which is 0, which means the delta v is 0, which means the velocity is not changing. Okay, so if the velocity is not changing, we know the velocity time graph should be a flat line. We have drawn a flat line for positive velocity, but really it can be any velocity. It can be a 0 velocity, positive velocity, or negative velocity. We'll just assume it's a positive velocity for this example. Okay, so we got the velocity time graph. Then we find the slope of the, we find the area under the velocity time graph to get the position time. Okay, so here they have constant velocity, and we know that we can slice this up like we did a few slides ago. We can draw slices, find the area of each slice, and make a plot. We'll get a position time graph that's linear, so kind of like this here. So you can see we have positive velocity, that's why this position time graph is sloping up. All right, so a special case here, if there's 0 acceleration, velocity time graph is horizontal, and position time graph is a straight line. And now let's look at what happens when the acceleration is constant. Okay, so suppose acceleration is positive and constant. It's a flat line, like in the first picture. So you find the area under this flat line. So you can make up slices like we did before, and then find the area of the slices. Then plot the graph for the velocity, and we'll see the velocity will be a straight line. So this is very similar to what we did for velocity and position up here. You just use the same principle that if you have a flat line for acceleration, the velocity should be a straight line sloping up. Okay, now let's look at the third graph here. If the velocity is sloping up, so the velocity is not constant, it's accelerating upwards, what does the position time graph look like? Let's find out. Okay, so let's start by looking at a picture of this setup. So this is a picture of the motion diagram of some particle that's moving to the right and is accelerating. So it's getting faster and faster, so the dots are getting more spaced out. So the velocity time graph looks like this, and you break it up into slices like before. So these are 5 slices of equal time that we chose, okay? And you can see in the picture, the slices don't have the same area. Obviously, the slice on the right has the biggest area, and it gets smaller to the left. And that kind of makes sense because you can see the velocity is getting bigger. So if the velocity is getting bigger, it means their object is traveling faster, which means the area under, which means the displacement, should be getting bigger and bigger as well. So faster speeds have bigger displacement, as we expect, and these are all equal time intervals. So we'll write it like this. The area, all these areas A1 through A5, represent delta x, the displacement. And since A5 is the biggest, the displacement in this last section, last interval is the biggest, and then gets smaller in the other intervals. Okay, so we know how the displacement changes. So we have to make a plot of position and time. So in the first interval for x1, delta x1, we should have a small displacement. Then the displacement should get bigger for the other intervals. Okay, so we do it like this. So suppose you start from 0, initial position, and then for the first interval, you go up by delta x1, a small number. For the second interval, you go up higher. You can see that we went up by a bigger delta x this time. And then the third interval, delta x3, is even bigger and keeps going up for delta x4 and delta x5. So you can see that this delta x's, they correspond to the areas. So bigger area means a bigger delta x. So we got our data points, and now we just connect them with a curve. Okay, we can't connect them with a straight line anymore because you see the dots don't make a straight line. So you connect them with a curve, and that's your position time graph. All right, so if the velocity is increasing linearly, the position time graph curves up. So we say it's a quadratic curve. It changes as the square of the time. All right. So when acceleration is constant and not 0, velocity is linear and position is quadratic. Okay. So here are two examples. So on the left, on the upper left, we have a constant velocity going up, increasing, and the position makes a parabola sloping up. All right, so we have a parabola that's curving upwards. And then the next example, we have velocity that's becoming more and more negative. It's linear, but getting more negative. So the position should also get negative. It should still be curved, a parabola, but it's going to be curving downwards because the object is traveling in the negative directions with a negative position. All right. So let's do this example. We have a particle starting at x equals 20 meters. So that's the initial position at time of 0, initial time of 0, and moves with the velocity graph shown here. So this object has an initial velocity of 12 meters per second, then slowing down, and it goes to 0 velocity. So it stops at time 3, and then has a velocity in the negative direction. It moves in the opposite direction. We are trying to figure out the position of the object at time 2 and 3 and 4 seconds. Okay. So let's start with the first box, time 2 seconds. So we are trying to find the displacement from 0 to 2 seconds. So you draw a line. Here, let's do it here. So you draw a line at 2 seconds all the way down to the time axis. Okay, and then you find the area enclosed like this. Okay. So this area is the area of under the graph between 0 and 2 seconds. It represents delta x between 0 and 2 seconds, right? So how do you find the area of this section? You break it up into a rectangle and a triangle. So what's the area of the rectangle? You multiply the base and the height. You multiply 2 times 4. You get 8 meters. Let's write this down. And what's the area of the triangle? So you multiply the base and the height and also multiply by half. Okay, so it's done in the calculation is done here. So you multiply half with the base, that's 2, and the height is 8. So you do half times 2 times 8, you get 8 meters again. So you get a total of 16 meters as your delta x. But the answer is not 16 meters. The answer is asking for the object's position. Okay, so the answer should be the object's position. So the initial position is 20 meters, and the delta x is 16 meters. So if you know the initial position, you can find the if you know the initial position and the delta x, you can find the final position from this equation, right? And this equation really comes from here. Let's write this down. This equation really comes from the equation that we had for delta x. So delta x equals x final minus initial. And when you rearrange this equation, solve for x final, you get x final equals x initial plus delta x. So for 0 to 2 seconds, delta x is 16 meters, and your x initial was 20. So you add 20 and 16, you get 36 meters. So that's your answer. Then let's also do part B before with the other one. So the question is asking, when does the particle have a turning point? So what's the turning point? When it switches direction. Or in other words, when the velocity becomes 0. Okay, okay, because the velocity starts at positive and then goes down. So at the point the velocity becomes 0, the object is turning around, okay, so it stops and goes in the opposite direction. And we can see from the picture it's at time of 3 seconds, the particle is the turning point. Then let's go back to the other two blanks here. We are trying to find the displacement at 3 and 4 seconds. So same idea. For 3 seconds here, let's do 4 seconds. Yeah. So for 3 seconds, you just find the area of this big triangle from 0 to 3. But if you're doing from 0 to 4 seconds, you'd have to find the area from 0 to 3 and then also the area from 3 to 4. Okay, so here, when you're doing 4 seconds here, you have to find the area from 0 to 3, which is going to be a positive number, going to be 18. Okay. So here the area is 18 meters. But then from 3 to 4, the object has turned around, it's going in negative direction. It has a delta x of -2. All right, so when you find the combined displacement from 0 to 4 seconds, you have to do 18 minus 2. You get 16 altogether. Okay, so let's write this down. So delta x would be 18 minus 2 equals 16 meters. All right, and that's the displacement delta x. You add it to the initial position to get the position, final position of 30. Okay, so now last thing here. So let's look at the concept of instantaneous versus average velocity. So here, the first graph on the left, we have a velocity that's increasing consistently by a straight line. So the velocity is different at different points. So you can choose these different points here, like 1, 2, and 3. So they will have different velocities, v1 and v2 and v3. These are instantaneous velocity. So the velocity at one instant of time. Okay. Now, suppose we don't want to find the instant velocity. We want to find the average velocity. So how do you find the average velocity? So yes, average velocity is the velocity averaged over a time interval. Okay, and here are a couple of equations that help you calculate the average velocity. So if the acceleration is constant, the average velocity is the same as initial velocity plus final velocity divided by 2. Okay, so we'll see that again later when we look at the equations of motion. If the acceleration is constant, average velocity is half of initial plus final velocity. And if the acceleration is 0, then the average velocity is the same as instantaneous velocity because the velocity is not changing. So V initial and final are the same. All right, so two concepts, instantaneous and average velocity.